Hello, it's Keith here, and this is lesson 1 of the so-called MinTile series of my 6502 assembly programming tutorials. What's MinTile? Well, what MinTile is what you can see on the screen here. It's basically a simple TimeUp system. It's a multi-platform one. You can see the PC Engine version here, but it basically supports all of the systems in my 6502, Z80 and 68000 series. It allows us to draw a tile map on the screen in a common way on all of the systems, whether they're hardware tile map like the PC Engine or software tile map like the BBC. We can run it on both. Now, it doesn't really use sprites. It doesn't use hardware sprites on the majority of the systems, but what it can do is it can use the tile map to simulate sprites. So this Chibico character here is actually being drawn with the tile map, but it's being used to simulate a sprite object, if you want to put it that way. The reason it's doing that is that by using the same graphics code to draw tile maps and sprites, we only have one piece of graphics code. It makes it easier to port the program to multiple systems. So that's what we've done. Another thing that's quite unusual, if you will, about MinTile is it only uses a single buffer. So on some systems you have some slight flicker as the screen redraws. It's fairly minimal though, and by using only a single buffer, it allows us to use less memory for systems like the BBC, which only has 32k of RAM in a lot of cases, and of course some systems have even less. So by not requiring a double buffer, it gives us more flexibility with regards to the platforms we've got to cover. Now we're going to start looking at the basics today and see the early parts of the code, and we will very quickly look at part of the platform specific code just so you understand what it is, but that will be mostly covered in other tutorials. Okay, well, let's go over to the code and let's take a look. Right, so the first thing we're going to be looking at today is the clear screen routine. Now the clear screen routine basically redraws the entire tile map. Now the way the tile drawing actually works is we have sort of three things we need to consider. There's firstly the bitmap data on the screen. That is what we are going to be drawing to. Then we've got the tile map data that is the background effectively. This is slightly wider than the screen. The screen is 32 tiles, but the tile map is 36 tiles wide, so that we can scroll 1 4 tile block before we need to actually recalculate everything. So that's the actual tile map, but in between the two there is the tile cache. The tile cache is the redraws that need to be made, the tiles that have changed and need to be redrawn to the screen. This is part of the fact that we don't have a double buffer. So rather than having two bitmap buffers, we have a tile cache that is the changes we need to redraw. And so when the screen scrolls, if we know that the old tile and the new tile, as we've scrolled one tile, are the same, we don't need to draw that. And if the sprite moves, we only need to redraw the parts that are underneath the sprite, and that is what the cache does. Now the clear screen routine is going to redraw that cache to the screen. So the first thing we've got to bear in mind is we've got various entries in the 0 page here, and we've named these, and so H and L are a pair, known as HL, B and C are a pair, and then we've got these S versions, which are a secondary version. Now these are of course based on Z80 registers. On the Z80 we have a HL pair and a DE pair, and we also have a shadow DE pair, so DS and ES are simulating that shadow pair. Now I know that might not be ideal for the 6502 programmers, but this is ported from the Z80. I'm primarily a Z80 programmer, so I'm afraid I have to work in a way that is easy for me to convert between systems, so that's why we've got that. So basically when we run this routine, we have DE pointing to our tile map. We've got DE apostrophe pointing to our pattern data, that is the bitmap data on bitmap systems, or the address of the first tile pattern on hardware tile map systems. We've got IXH and IXL, which are the width and the height of the drawing area. We've got IYH, which is the tile map width, and we've got HL, which is the VM destination. Now IYH is the width of the actual area, not the width of the drawing area. And some cases we might be doing cropping, that's why that's different. So the first thing we're doing here is we're basically moving the pattern data into the shadow DE pair. So we're just transferring that across there for later. We're moving DE to the shadow BC pair. That is the tile map source, so that's the source tile map. And then what we're going to do next is we're going to define our drawing area. Now we're going to draw a total of 24 tiles, so we're loading the value 23 into IXL here. That's the height. Now before we do a line, what we do is we load in the screen base into the HL pair here. This is the VRAM destination. This is platform specific, So for example, on the BBC, the screen base is maybe just 5000 in this case, the way it's set up. So that will be correct for the system. And then we are going to do the line drawing. Now, the line drawing basically consists of us setting the line width, which might be 32 or it might be less on some small screen systems. And then we run the do strip routine, which is the platform specific code, which will actually draw the line to the screen. Let's just quickly take a look at one. We're going to look at it in more detail later on in a separate series. But basically, our do strip routine here. Here is our do strip routine. What it's basically going to do is it's going to read in tiles from the source here. If they are 0, it's not going to draw them. A 0 in the cache means that the tile has not changed, so there's nothing to do. Otherwise, what it's going to do is it's going to calculate the bitmap source. This is the BBC version, so this is a bitmap screen. So it's calculating the bitmap source here into HLS. And what it's going to do is repeatedly read in bytes from the source pattern data, HLS, and write them to the screen data, HL. It's doing that repeatedly, and it does it 16 times, which is one full tile on the BBC. The BBC layout goes down and then across, so doing that will draw an entire tile to the screen. And then what we're going to basically do is we're going to repeat until we've done the entire strip of tiles, and at that point we return. Now after we return though, there will potentially be some fix-up needed to the HL destination screen address. Okay, so once we've done our drawing, we now need to basically fix things up. Now on the VIC and the links, they have a smaller screen, so we've not actually drawn the entire 32 wide tile map, so we're correcting BC for that. But apart from that, what we need to do is, depending on the system, we need to update the HL pair so that they move down to the next line. Now, the reason we didn't do that in the draw line routine is usually if we're drawing sprites and things, we won't draw a full line. And so we don't want to just assume that we want to move down one full line. In some cases we might be in exactly the correct position just by doing the natural increment commands. In other cases we might need a small adjustment. In some cases we might need a more complex one. But the routine for drawing the sprite, moving down a line for the sprite routine, is going to be different and could be quite a bit more complicated. So it didn't seem appropriate to make any assumptions on what the draw line command should do after it completes its line. And so here we've got the platform specific code to correct the HL pair to move down to the next after we've got to the far right hand side of the screen. And so that's what we've got there. Now once we've done that, all we've got here is basically we're decrementing the IXL, which is the Y line count in tile strips, and we're just repeating, jumping back all the way up to here, and what we're going to do is we're going to do the next strip from there. So that's how we are doing our lines. Now that's the clear screen routine, which is going to be for drawing an entire line to the screen. But we do have one other thing. Now when we are drawing our so-called sprites to the screen, they aren't actually sprites. What they are is a miniature tile map. This is the Chibico character in tile numbers here, and we've got separate bitmap data for drawing it. And so what we're going to do is we're actually going to pass that to the sprite drawing routine, and that will draw the Chibico character to the screen. So here is the draw tile map version, which is for custom sized tile maps. Now once again we are prepping the source tile map data into BC here, and what we're going to do is we're basically going to draw each line of the tile map, but then we're going to update our coordinates accordingly. So what we're going to do first is here we're checking the strip routine. This is for systems that don't support self-modifying code. We've got two versions, do strip and do strip reverse. That's for the X flipping operation. So do strip reverse is obviously the X flip version. So if we're running from ROM, we will run one of those via basically checking the strip routine byte here. If we can use self-modifying code though, we will use this do strip version here, and we will self-modify that into the reverse version where required. Now we are pushing HL, our VRAM destination, and DE, our tile map source, at the start here, and then we're popping them back here. Now why are we doing that? Well, our tile map might be cropped, and our screen, we're not at the end of anywhere. We don't know where we are because the position of the sprite will change. And so what we're going to do is we're going to manually fix those up, and this is why this isn't done as part of the do strip routine. So what we've got here is basically a routine for each system to move us down 8 pixels from the original starting position. So if our starting sprite position was here, we've drawn the line, we then move down, we draw the line, we then move down, draw the line, and so on. So this is a routine to move us down 8 pixels, and this is going to typically assume that we're aligned to an 8x8 block boundary. It depends on the system what's efficient. The BBC really isn't very efficient at moving at any other vertical strip amount, but as I say, that it will depend on the system. So that's what we're doing there. And then once we've done that, basically what we're doing is we are going to just repeat. We're taking the DE pair here and we're adding IYH, which is the width of the source tilemap before any cropping, because again, we can't assume we've got to the end of a line of our source tilemap, because if it's half off screen, it won't be. And then we're just repeating for the next line. Now, as I say, we do need the ability to X-flip our tilemaps so that our chibi code can turn the other way. So what we're going to do is, when we want to do that, is we run this do tilemap reverse, which will modify the code accordingly, and it will basically flip everything around. Now, what we do in that case is we still draw left to right onto the screen, but we process the tilemap backwards. So if you think of our chibi code character here, normally what we would do is we'd start from this here and we'd go across that way. But in the case we're drawing it reversed, we're going to go backwards from right to left. And so that means we can draw from left to right, and we're reading the data in from right to left. And we're flipping in software the pattern data of the tiles themselves. So that's what we're going to do. So to allow for that, we are updating the DE source, that's the source tilemap data, by adding the width of the tilemap, subtracting 1, so that we've moved to the end of the first line, and then we will process that backwards and then move down 1 each time. And then what we're doing next is basically we are going to self-modify our code if we can. If we're using self-modifying code, we're writing the reverse address into the call. So this will basically modify, where is it? So this will basically modify that do strip routine there. There's a calculation, subtracting 2 from that address, the line afterwards, and writing the address of the call in there. So that will correct that. If we are in ROM and we can't use self-modifying code, we're setting the strip routine to 1. We're then doing our draw tilemap, which will now work in reverse. And then we're setting everything back to normal, so that we're assuming that we are drawing unflipped. And so we're setting the routine back here before returning. And that's how we are drawing a custom tilemap, and we're allowing flipping. Now that's all we're going to be covering this time, but next time what we're going to do is we're going to take a look at some more of the sprite routines. We're going to look at the cropping routine and the routine that calculates the memory addresses that actually calls that do tilemap routine. That is just the drawing routine once everything's been calculated, but there's a lot of calculations that need to be done before we can do that. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.